In this video, we'll work through an example problem for a one-sample t-test. A trade journal article reports that mean purchase price of homes sold in Cleveland last year was $210,000. We wonder whether the mean purchase price in Buffalo was any different. To find out, we'll draw a random sample of 30 homes from the population of all homes sold in Buffalo last year. We'll use the standard significance level of 0.05 for our hypothesis test. The population of interest is all homes sold in Buffalo last year, and the parameter is the mean purchase price of those homes, mu. The appropriate hypothesis testing procedure for problems involving one population mean is the one-sample t-test. Random sampling assures that homes sold in all areas of Buffalo have a chance of being selected into the sample. This is important because we know that homes that are otherwise identical will sell for more in some areas than in others, and we want to make sure that the entire city is fairly represented. The independent observations assumption has to do with statistical independence. We need to make sure, for example, that no house was sold more than once this past year, or we'd have values that are not statistically independent. We would also want to make sure that the houses aren't all in the same neighborhood, because housing prices would be related. Random sampling comes into play here because it assures that all homes sold in Buffalo last year have a chance of being selected into the sample. So we'll say that this assumption has been met. The last assumption is the population distribution of purchase prices is normally distributed. Because the sample size is large, the central limit theorem is invoked, meaning that the sampling distribution of the mean will be approximately normal regardless of the shape of the population distribution. The null hypothesis is that the mean purchase price of homes sold in Buffalo last year was $210,000. And the research hypothesis is that it wasn't $210,000. We didn't specify a direction for the difference, so this is a two-tailed test. The model that represents the null hypothesis is a sampling distribution of all possible values for x bar when the null hypothesis is true. The mean, mu x bar, is equal to the population mean, and its standard error is estimated by dividing the sample standard deviation by the square root of n. Because the calculation is based on sample data, we can't determine the standard error until we collect our data. Here is the sampling distribution. The x-axis shows all possible values for x bar standardized to t values. The last piece of information we need is the degrees of freedom for this distribution. The sample size is 30, so the degrees of freedom is 29. For a two-tailed test, the rejection region is split evenly into the two tails. We need to consult a table to determine the critical values of the test statistic. Critical values for t are based on two factors: the significance level and the degrees of freedom. Degrees of freedom are listed in the first column, and each row contains values for one specific t distribution. This row gives values for a t distribution with 5 degrees of freedom. At the top are two sets of significance levels, one for one-tailed tests and one for two-tailed tests. After 30, the degrees of freedom skip to 40, then 60, 120, and infinity. At infinity, t is equal to z. We're doing a two-tailed test. We find 0.05 under two-tailed significance level and 29 degrees of freedom to get the critical value of plus or minus 2.045. We then add the critical values to the model. Any test statistic value that exceeds plus or minus 2.045 will lead to the rejection of the null hypothesis. Now we collect the data and find a mean purchase price of $182,000 with a standard deviation of 45,000. The t-test tells us how far away, in standard deviation units, our sample mean is from the mean of the distribution representing all possible sample means when the null hypothesis is true. Plugging in the data, we get a test statistic value of minus 3.41. This value falls within the rejection region, so the null hypothesis is rejected. In real life, we let statistical packages do the heavy lifting, and the focus shifts from the calculated and critical values of the test statistic to a comparison of alpha and p-values. Let's look at SPSS results for this study. The first table shows descriptive statistics, the sample mean and standard deviation, as well as the standard error. The next table shows the t-test results. We need to provide the value from the null hypothesis so that SPSS knows what standard we're testing against. Otherwise, the test value is assumed to be 0. These are the test results, the calculated test statistic t and the p-value. SPSS calls the p-value sig, which you should never confuse with the significance level. SPSS only produces two-tailed p-values, so if you do a one-tailed test, you have to divide this value in half. The last portion of the table provides a confidence interval. This is only interpreted when the null hypothesis is rejected in order to obtain a better guess at the value of the population parameter. By default, the confidence coefficient is set at 0.95. This interval is the best guess of the difference between our results and the value hypothesized under the null hypothesis. So we can say that we are 95% confident that the mean purchase price of homes sold in Buffalo last year was between about $11,200 and $44,800 lower than that reported for Cleveland. If we want to estimate the true purchase price of homes sold in Buffalo, we add the test value to both the lower and upper bounds. We can then say that we are 95% confident that the true purchase price was between approximately $165,200 and $198,800. There are a few ways that we could write up our results. First, we could say that the mean purchase price was significantly less than $210,000. We could also say that the mean purchase price was less than that reported previously for Cleveland. Degrees of freedom can be reported either in parentheses or as subscripts. We summarize the estimation results by stating that we are 95% confident that the true purchase price of homes sold in Buffalo last year was between about $165,200 and $198,800. In the next video, we'll look at two more examples using SPSS.